Welcome back to the channel. In this video, we'll learn one of the most important concepts in digital communication, line coding. We'll go through 8 popular encoding techniques used to transmit digital bits over a physical channel. These include polar NRZ, polar RZ, unipolar RZ, Manchester, differential Manchester, AMI, HDB3, and B8ZS. I'll explain each one with a simple example and guide you on how to draw the waveform step by step so you can easily recreate them in your notes or exams. And zeros, but wires and channels carry voltages. Line coding is simply the rule that converts digital bits into electrical waveforms. Different line codes help reduce errors, save bandwidth, and allow the receiver to stay synchronized. Let's start with the simplest, polar NRZ. Here, each bit is represented by a constant voltage for the entire bit period. A1 stays at a positive level. A0 stays at a negative level. That's it, no return to zero, no transitions unless the bit changes. How to draw? Draw a horizontal line at +A for every 1, and a line at A for every 0. Only change the level when the bit changes. In polar RZ, RZ means return to 0. So instead of staying high or low for the whole bit, the signal returns to 0 halfway through. How to draw? For a 1, draw positive voltage for the first half of the bit and 0 for the second half. For a 0, draw negative voltage for the first half, then return to 0. Unipolar RZ uses only positive voltage and 0. A1 becomes a short positive pulse, only for half the bit. A0 is simply 0 the whole time. How to draw? For a 1, draw a short positive pulse at the beginning of the bit, then drop to 0. For a 0, draw a flat line at 0. Next is Manchester coding, famous for being self-clocking. Every bit has a transition exactly in the middle. For a 1, the signal goes from low to high. For a 0, the signal goes from high to low. How to draw? Divide every bit into 2 halves. For 1, draw a downward segment then upward in the middle. For 0, draw upward then downward. The mid-bit transition is guaranteed. That's what helps with synchronization. Differential Manchester also has a guaranteed mid-bit transition, but the data is encoded based on what happens at the beginning of the bit. If there is no transition at the start right pointing arrow, the bit is 1. If there is a transition at the start right pointing arrow, the bit is 0. How to draw? Always draw a change at the middle of the bit. At the start of each bit interval, decide whether to switch levels or not based on the bit value. AMI stands for alternate mark inversion. Here, all zeros are simply 0 volts. But ones alternate in polarity, +A, then +A, and so on. This reduces DC content and makes the signal more balanced. How to draw? Write the bit sequence. Whenever you see A1, alternate between positive and negative pulses. Zeros remain at 0 volts. HDB3 improves AMI when long runs of zeros appear. Because too many zeros mean no transitions, the receiver may lose synchronization. So HDB3 replaces every 4 consecutive zeros with a special pattern that includes a polarity violation. How to draw? Start drawing like AMI. Whenever you see 4 zeros, substitute them with either B00V or 000V, depending on the polarity history. Draw the V pulse as a violation, meaning same polarity as the last pulse. B8ZS is similar to HDB3 but used in North America. Whenever we find 8 zeros, we insert a fixed pattern that includes 2 bipolar violations. This guarantees transitions so the receiver stays synchronized. How to draw? Draw AMI normally. When you hit 8 zeros in a row, replace them with the B8ZS pattern. Mark the violation pulses clearly. They have the same polarity as the previous pulse. Now that we've seen all 8 codes, it's important to know how they compare in bandwidth. From highest to lowest bandwidth, polar RZ, unipolar RZ, Manchester, differential Manchester, HDB3 and B8ZS, AMI, polar NRZ. RZ and Manchester require more transitions, so more bandwidth. NRZ has fewer transitions, so it occupies the least bandwidth. To recap, NRZ codes hold voltage for the entire bit. RZ codes return to 0 mid-bit. Manchester codes ensure a transition for every bit. AMI alternates polarity for ones to reduce DC. HDB3 and B8ZS fix long zero runs using violation patterns. These encoding schemes form the foundation of digital communication channels. Understanding how to draw and interpret these waveforms is essential for exams, lab work, and networking fundamentals. Thanks for watching. If you want downloadable waveform diagrams for each encoding type, just comment below and I'll share them. Don't forget to like the video, subscribe, and hit the bell icon for more communication system tutorials.